Okay, so as promised, I will try to create a flip video about going through tomorrow's homework or today's homework assignment. But I put a new homework assignment on D2S, so first read that. Okay, so I have put some similar problems, and then let's see whether we can try to do similar problems. Okay, and then let me explain it. Okay, all right. Let's take the. So here are some problems. Okay, so let's take the first one. So the first one we want to check whether it's absolutely convergent or conditionally convergent. Okay, so the best advice that I can give you is to use the two-step process. First of all, check the convergence of the series itself. In order to do that, you usually try either the the AST or the root test or the ratio test. But right now it's very clear that AST is suitable here. But let's see. Okay. Now this is the widget part. So step one, we want to check whether the series is convergent. So this is the widget part. This is the remainder part. Now don't let this point 2 deceive you, because point 2 is actually what is point 2 is 1/5. So this is like 1/5 to the power n. So the widget part is 1/5 to the power n, right? Okay, and if you look at that, okay, because that can be written as 1 over 5 to the n. So the remainder part is 1 over 5 to the n, and because we have 5 to the n in the denominator, that will go to 0 and decrease. So this part, actually the remainder part, decreases to 0 because it's 1 over 5 to the n. Therefore, by AST, the series itself is convergent. So step 1 is convergent. All right. By the way, if step 1 is divergent, then you don't have to go any further, because then you can't even talk about conditional or absolute convergence. Now let's go to step 2. So in the step 2, you take the absolute value of the series. So absolute value series. So then this widget goes off, and all you have is 1/5, right, to the power n. So we have the series just a sigma 1/5 to the power n. And what about that series? So if you have that series 1/5 to the power n, right, then we clearly know that that series is a geometric series, isn't it? So, and the common ratio is 1/5. And because the common ratio is 1/5, the geometric series is convergent. So the absolute value series is also convergent. So step 2 is also convergent. So step 1, the full series is convergent, and step 2, the absolute value series, are both convergent. So this series is absolutely convergent. Step 1 and step 2 are both convergent. Okay. Now let's go down to problem number 2. So once again, let's apply, because they are asking for absolute conditional convergence, right? And we have the -1 to the power n widget, right? Let's try step 1 and step 2. So step 1 is to try the full series. So once again, we start with the AST. So we have the widget here, right? The alternating widget, right? And then we have the remainder part, right? So it's very clear that the remainder part is decreasing, and then if you take the limit of this, it's 1 over infinity, so it's 0. So we have the remainder going to 0. So that means it is actually okay from AST to say that this series, the full series, is convergent. Now let's look at the absolute value series. So if you look at the absolute value series, then just forget about this part and just concentrate on this part right here. So what about that series? So when you have a situation like that, it's always good to look at a partner, a comparison partner for the limit comparison. So as I mentioned, when you look at the partner, you look at the highest power and you ignore the constant. So the highest power here is n, but remember there's a square root outside, so it's square root n. So 1 over square root n. So that is like 1 over n to the 1/2 power, right? Square root. So 1/2 is less than 1. So by the p-test, we can say that 1 over square root n sigma is divergent. So we found the absolute value series divergent here. So step 2 is divergent. So step 1 is convergent, step 2 is divergent. So the full series, the original series, is conditionally convergent. Now let's go to the third one. Now the third one, again, let's look at step one. So we look at step one. Let's try the AST first, right? So we have the negative 1 to the power n, that's all right. And then we have this part, the remainder part. The widget part is this, the remainder part. So what about the remainder part? First of all, it should decrease. Well, you have n squared and n fourth, right? So it will definitely decrease. But the question now is whether the limit will go to 0. Well, how do you find that out? If you, well, you can use the L'Hopital's on this one. And then if you differentiate first, you get 2n. And then you get 4n cube, right? And then you differentiate it again. The 2n becomes 2, right? And the 4n cube will become 12n squared, right? But it doesn't really matter. So you will have 2 over 12n squared, which is 1 over 6n squared. And that is like, will go to, the top will go to 1, the bottom will go to infinity. So it goes to 0, okay? So by L'Hopital's rule, okay, this part will go to 0. Alright, so we have the remainder part going to 0. So part 1, let's once again, so we have the widget and the remainder part going to 0. So therefore by part 1, this thing is convergent. Now let's look at part 2. In part 2, we look at the absolute value series. So when we look at the absolute value series, the widget, the alternating widget goes off, and we just have, you know what, you have n squared over n to the 4 plus 1. Okay, so then if you have n squared over n to the 4 plus 1, what do you take from that? Well, if you look at that, can we look for a partner here? If you look at the comparison partner, the highest power on top is n squared, the highest power on the bottom is n to the 4th. So the comparison partner will be 1 n to the n squared over n 4th, right? Which is the same as, like, we cancel this out, you get what? 1 over n squared. So sigma 1 over n squared, right, is the comparison partner. Sigma 1 over n squared is convergent. Okay, alright, so the absolute value series, which will be this series and this without this, right, it's convergent. So part 2 is convergent. So part 1 is convergent, part 2 is convergent. So that means the series is absolutely convergent. Now let's go to number 4. Once again, let's try the AST for part 1. So you have the widget, alternating widget here, and the remainder decreases to 0 clearly. The limit of this is 0. So this is clearly convergent by AST. Now if you look at the absolute value series, then this goes off. And then you have 1 over n plus 5 sigma. So what is that? Well, we'll look for the partner. So clearly the partner is 1 over n. So sigma 1 over n. Now please do not get deviated. Sigma 1 over n is definitely divergent. Okay. Alright, so the partner is divergent, so the series is divergent, so the absolute value series is divergent. So we have a conditionally convergent series. Alright, now let's go to the second set of problems that I have. Alright, so this one right here. So once again, let's look at the first part. Okay, now part 1, let's try to see whether I can use the AST here. Well, the alternating widget is there, but take a look at this one. Now, this looks kind of so suspicious, isn't it? Because, right, it doesn't, the top has n squared and bottom has n squared. So the remainder is this for the AST. Does the remainder go to 0, the limit of the remainder? Well, it doesn't look like, right? Why? Because if you differentiate the top, you get what? 2n. And you differentiate the bottom, again you get 2n, and the 2n and the 2n cancels off, and you actually get 1. So the limit of this is 1, not 0. Then AST will not work. Then what will work? I told you, as soon as the AST doesn't work, look and see whether the divergence test will work. Well, see what happens now is that if you look at the limit of this sequence, the full sequence right here inside the series, right, then because this part goes to 1, right, it looks as if this will eventually go to a situation between -1 and +1. It kind of oscillates. The divergence will oscillate between, okay, the even terms will head towards 1 and the odd terms will head towards -1. So it's divergent, right? So definitely it is not equal. The limit is not equal to 0 in particular, right? Okay. So because the limit is not equal to 0, by the divergence test, this is divergent. So this series is divergent. Part 1 is divergent. So remember, if part 1 is divergent, that's the end of the story. There is no point going to part 2, which is only makes sense if the part 1 is convergent. So part 1 is divergent. So the answer is the series is simply divergent. Remember that only 3 things can happen. Either a series can be conditionally convergent, or a series can be absolutely convergent, or a series can be divergent. There is no such thing as conditional or absolute divergence. That is only for convergence. So we look for conditional absolute only if the part 1, the series itself, is convergent. Let's go down, guys. So now we have this one right here. So AST. For this one, so we have the alternating widget, and then the remainder of that will be what? This part. So this is a remainder for the AST. We need to see whether this is decreasing. Well, it is decreasing because this is bigger than this, right? But that is a limit equal to 0. Well, how do you find the limit of this? Well, you can use the L'Hopital's again, and then if you differentiate the top, you get what? 3. And you differentiate the bottom, you get 5n to the 4. So you get 3 over 5n to the 4. So there's an n to the 4 in the denominator and a constant on top. So that definitely will go to 0. So by AST, right, the remainder goes to 0. And we have the alternating widget, so the whole thing is convergent. Now let's see what happens to the absolute value series. So if you take the absolute value series, right, okay, the absolute value series is the widget. You can just forget about the widget. Okay, widget is no longer there, so you just have this one. Okay, so you look at this, look for a partner. So if you look for a comparison partner, what do you have? On top, the leading power is n, the bottom, the leading power is n to the 5. So if you simplify that out, you get 1 over n over n to the 5, which is 1 over n to the 4, and sigma 1 over n to the 4 by p-test is clearly convergent. So the absolute value set this is convergent. So guys, so this is definitely part 2 is convergent, part 1 is convergent. So what are we looking at? We are looking at the convergence series. All right, so now if you look at the third one, right, let's go through this very quickly. Right, now if you look at the part 1 of that, if you try to use AST to this, right, the question is whether we will get the alternating widget is there. Now what about this part? Does it go down to 0? If you look at this carefully, right, now 1 over 4 to the n can be written as 1 over 4 to the n. Right, so really this is what? This is like n to the 3 divided by what? 4 to the n, isn't it? So it's really, you can forget about this part and think of this as n to the 3 divided by 4 to the n. Well, if you really look at that, right, n to the 3 grows much slower than an exponential, which is 4 to the n. 4 to the n is exponential, so the bottom dominates significantly. So n to the 3 over 4 to the n, the bottom dominates significantly, so it goes to 0 very clearly. So the full series is convergent. If you look at the absolute value, then you just don't have to worry about that. You have n to the 3 over 4 to the n. And then how do you handle that one? Well, you can do many things, right? Okay, so you have n to the 3 over 4 to the n. Okay, all right, so sigma n to the 3 over 4 to the n. One of the things you could do is you can actually use the ratio test on that case. So we need to nail n to the 3 over 4 to the n, right? So if you use ratio test, okay, bear with me while I try to simulate that. You have what? An plus 1 over an, which will be what? N plus 1 to the 3 over 4 to the n plus 1 divided by n to the 3 over what? 4 to the n. So when you take that up to the top, you will actually have n plus 1 to the 3 times 4 to the n on top. And at the bottom, you will have 4 to the n. So let me just, I can't write it on the screen, but let me try to see whether I can explain this to you without hesitation. So n plus 1 to the 3 over 4 to the n plus 1, and then you have n to the 3 over 4 to the n. If I take the 4 to the n right to the top, then I get n plus 1 to the 3 times 4 to the n on top, and then 4 to the n plus 1 and n to the 3 on top, right? Okay, and then What happens is 4 to the n will cancel off with one of the 4 to the n's. So you really have n plus 1 to the 3 over n to the 3 over 4. So you have n plus 1 to the 3 over n to the 3 over 4. Now, if you notice that, and if you use L'Hopital's rule, you can see that n plus 1 over n goes to 1. So the part goes to 1 to the 3 or something, and then you really have 1/4 as the limit. So work on that. So the limit, if you use ratio test onto this series, right, the limit of an plus 1 over an is actually equal to 1/4, which means it is convergent. So part 1 and part 2 are both convergent, so the answer is absolutely convergent. But actually we could have avoided part 1 and part 2 by simply applying ratio test for the full series. Because remember, if you take the ratio test with the absolute value, right, okay, then you will still get that limit. What limit? The absolute value of n plus 1 over an to be equal to 1/4, because this widget will disappear once you take the absolute value, which is less than 1. So without wasting our time on part 1 and part 2, you can nail this in one shot by using the absolute value form of the ratio test. So same deal here, guys. Okay, so but now what do I have here? So if you use the AST to this one, this is widget, the widget is there, and now look at the remainder part. Now very clearly, right, if you are going to use the AST, then the remainder part has to go to 0, but will it go to 0? Factorial is much faster, much faster than 2 to the n. So this will dominate and go to infinity. So this limit is actually infinity, so you can't use the AST. Then you immediately go back to the divergence test. Well, then very clearly, because you look at this thing, even though this will oscillate, because this thing goes to infinity, it is not, the limit of the sequence is not 0 in particular. So by the divergence test, this is divergent. So the original series is divergent, so there's no point, you can't even talk about conditional or absolute convergent. Alright, it's been quite a long video. I don't know whether I'll be able to upload it, but at least I'll try to see whether I can send a Dropbox link to the video. Alright, and so we'll stop here, okay?